All right, so last topic for this quarter is frequency response. Let's see. All right. Now, we'll use the techniques that we learned in chapter 5. We'll also use some background information from chapters 3 and 4, right? Because frequency response also depends on the capacitors and the inductors, so we need those basics. But we have talked about this before, where we have the signals all around us, whether wired or wireless, for all electronic circuits, electric circuits, the signals of time varying waveforms fall the entire spectrum from like 0 hertz all the way to like megahertz, gigahertz, and terahertz, right? We are primarily concerned with frequencies that we see in everyday life, going from like tens of hertz all the way to, let's say, 5 or 6 gigahertz, 5 gigahertz wireless router, right? So we've talked about how we have different signals all around us, most of it wireless signals. For instance, we have T-Mobile, AT, and Verizon, the 3 largest networks, well, in the continental US. They all operate within a particular frequency band, right? We have AM radio stations, FM radio stations, television stations that broadcast over the air. And all of them are operating at one particular frequency, right? So if we think of a highway, right? It's conveying cars, vehicles from one point to another point. So think of a wired connection or a wireless connection the same way. We have a source and we have a receiver at the other end. If you think of the data being transmitted from the source to the end being received, think of it as a highway that has multiple lanes. The frequency spectrum or the frequency bands that each of these applications work with is kind of a lane. So if you have an AM radio station that broadcasts at 680 kilohertz, it's using that lane of the highway. No other vehicle, meaning no other radio station or television station, is allowed to broadcast on that particular lane, right? But the question is, even though they're operating it within their own particular lane, their own operating frequency, those signals are all coming in at the same time. If you think about it, your cell phones right now, not only do they have to deal with, like if you have an AT&T cell phone, it has to deal with Verizon signals, it has to deal with T-Mobile signals, Sprint signals. It also has to deal with FM, AM, satellite television, over-the-air television. All of the signals are still coming into that cell phone. How does it not crash? And that's where the magic of electronic filters come into the picture. A filter, like a mechanical filter, electronic filter, like a mechanical filter, blocks out unwanted signals, meaning it does not allow anything else to come in except for that one particular frequency that we want to work with. So when you tune your radio station to 680 kilohertz, or if you pick up your cell phone and you're trying to make connection to your, to the cell phone tower, what it's doing is a filter is at the front end of that device. It blocks everything else except for that one particular frequency where it needs to make connection, right? So that's a real life example of why we need filters. Another real life example I can give you, well, it's basically this. This is, of course, fun. What does this remind you of? Anyone? You're all college students. If this is not familiar, you need to get out a bit more. It's a loudspeaker. It's a loudspeaker. Come on, I mean, I know my handwriting is worse than the doctor's prescription, but still, you're all college students. This should be familiar. What is this called? Well, a woofer. A subwoofer is, well, subwoofer would be, well, as the name suggests, below below the woofer frequency, sub, right? Below the woofer frequency. A tangent. Anyone have a subwoofer in their car? No one? Seriously, I'm disappointed in this generation. I had two in my car when I was in college. A cheap one from Walmart, $100, but still, man, you're also tensed. Mid range, and what is this called? Tweeter. Now, jokes apart, this is typically this is known as a loudspeaker box or a speaker box. These are known as speaker drivers. Okay, this one is a woofer, small one is a tweeter, and the rectangular one is a mid-range. Right, each one has a specific function. What it's doing is a woofer is specifically there to reproduce the low frequencies, the loud thumping bass sounds. Right, the the bass sounds. Whether it's a song, whether you're watching a movie, it reproduces low frequencies, a few hundred hertz or less. A subwoofer is highly specialized. The lower the frequency, the larger the cone of the speaker driver, and the more power it needs. So that's why subwoofers, like really good subwoofers, will cost you at least $300-400 or more. Like really good ones will go up to 1,000, like 1,000 and beyond. So really good subwoofer reproduction costs like hundreds of thousands of dollars. Anyway, tweeter reproduces high frequencies, basically the squeaking sounds, squeaking noises. Mid-range, mid frequencies, typically vocals. Right, each one of them requires a different wiring connection. But if you look at the back of this box, you will see a panel which has only like two connections, one red, one black, and you have one speaker cable, one wire or one cable that's coming in, one positive, one negative, right? So you only have one wire that's coming in. And that one wire, well, one cable consists of two separate wires, plus and minus. That one cable goes inside the box, but if you open up this panel, I mean, it's just like two screws, you can open it up easily. You will see that it is actually going into the box, into a circuit. It goes into a circuit. So it goes into a circuit. Again, this is just one speaker cable. And the circuit has three outputs. So the circuit has three outputs. So this one cable coming in is split three different ways. Now, this is known as a three-way loudspeaker. Most loudspeakers would be like two-way loudspeakers. You just have like a woofer and you'd have like a mid-range come tweeter. So then the signal would just be split into two. Okay. What this is doing is basically it's taking the incoming signal. The incoming signal could be a song, could be a movie, could be anything, right? When you have, well, human hearing range, typically we say it's like 20 hertz, 20 kilohertz. People like me, average listener, I mean, average listening spectrum, maybe like 50 hertz to maybe 10 or 15 kilohertz, not much beyond that, right? Anyway, so the incoming signal is probably somewhere from like 10, 20 hertz, going all the way up to 15, 16 kilohertz. It takes the incoming signal, splits it into three, and the low frequencies are sent to the woofer, the high frequencies are sent to the tweeter, and the mid-range vocals are sent to the mid-range driver. And this circuit is known as a crossover network. Crossover network. It consists of some resistors, capacitors, and inductors. So if you open up the back panel of any loudspeaker like this, and you pull it out a little bit, you'll be able to see that there is a speaker box. There's a circuit in there. It's a passive circuit, does not require any power. And it's known as a crossover network. The technical name for this crossover network is a filter. It's an electronic filter. It's an electronic filter, meaning it only allows a certain range of frequencies to go in a particular direction. So it's filtering out those frequencies. So the woofer line blocks the high and the mid-range frequencies. The tweeter line is blocking the low and the high, the low and the mid-range frequencies, and the mid-range is blocking out the low and the high frequencies. So each particular line only allows a particular frequency or a particular band of frequencies to pass through. Everything else is filtered out or it's blocked out. Okay, so that's a real life example of a filter. Now, what we're going to study, filter, as I said, filters are everywhere in all electronic components. Without filters, nothing would work. Nothing would work without electronic filters, right? I just said, like, just take the cell phone, for instance. You have like 3 major cell phone companies. They all work in a particular band of frequencies. These band of frequencies are known as a spectrum, the spectrum of frequencies. And the FC, it's known as a wireless spectrum. And it's very, very expensive to buy that wireless spectrum. It goes into billions and billions of dollars. The FCC auctions off a particular band of frequencies, and companies bid on those frequencies. Okay, companies bid on those frequencies to have the right to broadcast or own that particular lane, that particular band of frequencies and broadcast. No one else is allowed to actually broadcast in those frequencies. Otherwise, accidents would happen. Everything would crash. So again, without filters, nothing would work. Yes. No, nothing like that. That's just due to a combination of a lot of things. And just more traffic around the internet. If you compare it to like a normal like highway, is the same thing. A highway is already there, it has some capacity, but you have more traffic, everything slows down. So it's something like that, yeah. It's there's, even though we're talking about like wireless data transmission, there's certain capacity that a network has. If a lot of people are using it at the same time, it's not going to work. So if you go to like a, like a football game or like a basketball game or something where there are tens of thousands of people, if you try to use a cell phone there, it's not going to work as efficiently because there's so many people trying to use it at the same time. And so network is like jammed up. All right. So then let's get into what we're going to look at. Filter design is a very specialized topic in electrical engineering, right? It's a whole different subject. We're not going to do that. We're only going to look at the basics. What we're going to look at is basically a simple filters based on capacitors and inductors, which is what a crossover network would be. But again, filters are all around us. All the filters that we use in modern electronic devices, they are very, very complicated, right? They require very high level of design and high level of study. That's not something what we're going to do. We're going to look at the basics. So we need, before we actually begin to do that, I want to introduce how we're actually going to look at. So we need to look at the circuits a little bit differently. So typical circuit that we have looked at would look like this. You have a source, you have a resistor, maybe you have an inductor or a capacitor in there somewhere, right? Now, what we are going to do is we are going to separate out the circuit from the input and the output. Okay, we're going to separate out the circuit from the input and the output. So I'm going to say that I want to take the output either across the resistor or across the inductor. So in this case, for convenience sake, I'm going to say that I'm taking the output across the inductor. O/P is my short acronym for output. Okay, so it's output over here. And on the left, we have the input. What I'm going to do is I'm going to draw a line around or a border around the circuit and just show you a representation where we have a circuit and I have an input that's separated out on the left, output separated out on the right. Now, This is just standard practice over like decades and decades. Doesn't mean that the input is always on the left physically, right? It could be anywhere, but this is just standard accepted convention. We typically always have the input drawn on the left and output drawn on the right. But realistically speaking, it could be anywhere. So what do we see? We have an input signal. It has two terminals, plus and minus. We have an output terminal. Again, two terminals, plus and minus. Those two terminals put together form what is known as a port. Okay, so it forms a port. So here, I'm going to call this input port, and this would be my output port. And because it has two terminals, plus and minus, this would be a two-terminal, two-port network. Okay, two-terminal, two-port network. Again, in E major classes, when we teach circuit analysis, we have an entire chapter devoted to like just two-port networks, not just filter networks, but two-port networks, where we don't care what is inside the network. We are only analyzing from the perspective of the terminals. Okay. So we're going to look at circuits a little bit differently in this chapter. Make sense? Any questions? So how do filters work? This is a very, I wouldn't say rough, but like very basic analogy of how a filter would work. Okay. If you take a look at the signal, we cannot define it as a sinusoidal waveform, right? But using like mathematical analysis, we can show that any kind of signal in this world is basically a combination of multiple sinusoidal waveforms. So in this case, we take that incoming signal and we split it into two parts. We can see that it's comprised of input 1 on the left, input 2 on the right. Again, very basic example. We are saying that this incoming input signal only has two components. So what a filter does, again, it does not really split it into two, but this is just for explanation purposes. A filter is going to take both of those components independently, and depending on its function, it's going to enlarge or basically amplify one component, and it's going to attenuate or block the other component. Again, a filter is going to take an incoming signal. In this example, it only has two components. It's going to allow one component to pass through, and it's going to block the other component from going to the output. And then you have the output again, combined combination. So your input is up there. When it goes through the filter, output looks like this. This is input, and this is how it is transferred to the output. Input signal 1 is amplified. Input signal 2 is attenuated. Basically blocked and passed. Make sense? So again, very basic example, very basic analogy, but that's what a filter is going to do. It's going to take some components, going to allow them to pass through. Some components are going to be blocked. Now, depending on whether it's the frequencies are low or high, we have different kinds of filters. One point about this, here we can see it's attenuated, right? So depending on a design of the filter, this attenuation can go all the way to 0. It just depends on how the filter is designed. In an ideal filter, we can never have a sharp cutoff, right? We can never have like actual, like if you say that I have a filter designed for like 1 kilohertz transition, you can never say that it goes up to 1 kilohertz and then goes straight to 0. It does not work that way, right? Real life, it does not work that way. The other point about this input signal is you can see that it's larger, it's amplified, right? Now, what that means is that there is some sort of gain factor in that filter. Okay, So if the filter also has an amplification factor built in, if there is a gain built into the filter, we call it as an active filter. And if it's no gain, then we say it is a passive filter. And E non-major class, E201, we only study passive filters. We do not study active filters. Active filters use like op amps and stuff. So if you take E321, we'll learn about op amps. One of the applications for op amps is active filtering, where capacitors and inductors filter out the signals, and then the op amp performs the amplification or provides the gain. So gain is basically just multiplying an input signal, increasing the amplitude. Amplifier, basically. Anyone ever use a graphic equalizer, like the manual sliders on a boombox, or even in software, right? You adjust your graphic equalizer, or you adjust the bass or the treble. Anyone ever do that? That is an example, a real life example of an active filter. You're basically taking your incoming signal, and if you look at those sliders, it'll have a frequency band listed right next to it. You can check it out on your laptops. You can look at images on the internet, but there's a frequency band number that's listed on there. If you have a boombox which has those mechanical sliders, it'll have some frequency listed in there. So when you move the slider up, what you're doing is you're increasing the gain of that filtering of that particular bandpass filter. Okay, and you can immediately, of course, see the change in the speakers. You can hear the change in the speakers when you move those sliders up and down, right? The sliders on the left are the low frequencies. Somewhere in the middle is basically the vocals, and then as you move towards the right, it's basically the high frequencies. So if you want the loud thumping bass sounds, you increase the sliders on the left. That's basically a active filter. All right, transfer function. We have a two-port network, input on the left, V in, you got V out over here. Transfer function is a quantity that simply describes how the input is being transferred to the output. Okay, how V in is going to V out. And I named it after myself. Not really. I mean, I don't know why they've chosen H, but H of F basically describes how the input is being transferred to the output. It's simply a ratio of V out to V in, output voltage to input. What that also means in terms of the V out and V in equation is that V out is a product of the input and the transfer function. Okay, if we know the transfer function of a network or a circuit, we can predict what the output will be. We don't need to know what is inside the circuit. We don't need to know what is inside the network. We don't need to know what it's comprised of. It's a sealed box for us. But if we know what H of F is, we can predict V out for any given input. Okay, so let's say H of F, for example, is simply describing the gain, and the gain has 2. So then I can say if V in is 1 volt, V out will be 2 volts. If V in is 5 volts, V out would be 10 volts. I can predict what the output is going to be no matter what the input is. Make sense? Right? Yeah. 0.5. Yeah, it just depends on the circuit. application. Yeah. This is just a random example, like gain of 2. I mean, for filter, we are not going to look at that, but I'm just saying if it's a generic circuit amplifier, let's say, and the description is gain of 2, then we can predict what the output is going to be. What else do we notice? Yes. Square. Oh, yeah, that's the point I'm trying to make. What do we notice? Good question. What do we notice? What is this? It's phasors. It's phasors. So it has magnitude and it has phase, magnitude and phase. And h of f is a ratio of v out to v in. So h of f, the transfer function, is also a complex number. It's a complex quantity. It has magnitude and it has phase. So h of f is a complex quantity. It has magnitude and it has phase. And so to answer a question, it has peak values and it has a phase angle. And also it is dimensionless because it's a ratio of voltages. It's a ratio of voltages, no units. Make sense? Oh, okay. Now you do? Kind of. So if you're given h of f for any given circuit, we can find the output, right? Now, homework 17, which is no longer available on mastering, deals with transfer function problems. If we have time, I will finish it on Wednesday and then I will assign it. If not, I will eliminate that homework. So you don't have to worry about it. But I'm just going to go over, I'm not going to solve the problem right now. I'm just going to go over a brief explanation. This is a graphical representation of a transfer function. Plot on the left gives you the magnitude. Plot on the right gives you the phase. When you have an input signal, whether it has multiple components, like 2, 3, 4, 5 components, you look at the frequency of each component. At each particular frequency, you extract the magnitude and the phase of the transfer function, and you multiply it with the input phasor, and you can predict what your output is going to be. That is essentially how we're going to solve, predict an output for a circuit. Okay, so homework 17 deals with that. Again, if I have time, I will do this on Wednesday. Otherwise, we'll just skip it because it's not that important for the rest of the chapter. Any questions about transfer functions, the basic? I'm just doing like the basic setup before we move into actual filter circuits. Okay. So filters are primarily comprised of inductors and capacitors, right? Inductors and capacitors. Resistors, the behavior is exactly the same. It doesn't change with varying frequency. It's only the inductors and the capacitors that the behavior changes, right? So I call this my handy dandy table for quick and easy analysis of any filter circuit. And what we do is we approximate the circuit and we redraw it for 2 different kinds of frequencies. When frequency is very, very low and when frequency is very, very high. So when frequency is very, very low, I can plug in F or omega as equal to 0. When it's very, very high, I'll plug in F is equal to infinity. And I know that the impedance of an inductor is j omega L or j2 pi FL. ZC is 1 over j omega C. So ZL is directly proportional to omega or F, right? And ZC is inversely proportional to omega or frequency F. As the frequency increases, the impedance of an inductor increases. At extremely high frequencies, omega or F goes to infinity, meaning the impedance of the inductor also goes to infinity. If the impedance goes to infinity, it behaves like an open circuit. Make sense? Right? And when omega or F is equal to 0, impedance of inductor is 0, and so it behaves like a short circuit. I'm sorry, it behaves like a short circuit at very low frequencies. Does that make sense? Any questions? Right? It comes from these equations. And capacitor is exactly the opposite. When you have extremely low frequencies, capacitor behaves like an open circuit. That's where I talk about fundamentals, going back to chapter 3. When you apply DC, what happens to a capacitor? Reaches full charge, behaves like an open circuit. DC, F is equal to 0. Make sense? It all ties back together. So handy dandy table, you can have this table on your equation sheets. You don't have to, obviously, I don't want anyone just memorizing for the sake of, like rote memory. If you know or familiar with these equations, you can create this table anytime, right? You only have to remember ZL. ZL is J omega L, J 2 pi FL. Capacitor is exactly the opposite, 1 over F, right? So this table, again, do not have to memorize it. You can have it on your equation sheet, but you should definitely understand how to create the table. So when you have a circuit, when you have this kind of table, you can analyze a circuit within a few minutes. And based on the components, capacitors and inductors, we'll have 6 different kinds of filters that we'll study. There's not that many. These are the basic filters, okay? These are basic filters. When you have RC, okay, so we cannot build a circuit without a resistor, right? So when you have one capacitor and a resistor, we have an RC circuit or RC filter. Same thing with an inductor, we have a RL filter, right? If you have a L and a C together in a circuit, you have a RLC circuit or a RLC filter. So for a RC circuit, you can have a low pass filter and a high pass filter. RL circuit also, you can have a low pass filter and a high pass filter. Those are the 4 filters, 4 basic filters. They're the same circuit. You'll see they're the exact same circuit. There's no difference. And then the most important filter, band pass. Only allows a certain band of frequencies to pass through. Everything else is rejected. Every single filter that we use in everyday life is pretty much a band pass filter. Okay, the crossover network is a good example of where you actually have a low pass and a high pass. But for the most part, every other filter in every electronic device is a band pass filter. And then you also have something known as a band stop or band reject filter. Basically, it rejects a certain band of frequencies from passing through. Okay. Also, a word about the order of filters. RC and RL filters, how many energy storage elements? 1, right? Chapter 4, 1 energy storage element requires a first order differential equation. Hence, it is known as a first order circuit. So a RC and RL filter is a first order filter. So RC and RL filters are first order filters. A RLC, or a circuit that has more than 1 energy storage element, is a second order filter. So first order and second order filters. And again, filter design or filter study is an entire course by itself. Even EE majors do not take that course until, like, they're like senior year or even in graduate school. So it's a very specialized field. Here, I said a lot of things. Which one in specific? RC filters, you can have both low pass and a high pass, and it's the exact same circuit. RL is the same thing. You have a resistor and a capacitor. You have a RC filter. When you have a resistor and inductor, it's RL filter, and you can have both low pass and high pass RC filters. You have low pass and high pass RL filters. So we are studying 4 filters in all, but those 4 filters, they're the exact same 2 circuits. The same RC circuit will work as a low pass and a high pass, and I will show you how. Yes. Yeah, I think I need to make a change, kind of like maybe eliminate this line. I mean, the table itself is not important. It's just a way of like summarizing what kind of filters we're going to look at. That's basically what I was trying to convey. But it's kind of like a good point. Maybe I would eliminate that line and I know, yeah, RC and high pass or something like that. Oh, okay. That's a good question. Yeah. So you have a circuit that allows a certain band of frequencies to pass through. Everything else outside that band is blocked. That is known as a band pass filter. Now, if I plot the output voltage as a function of frequency, certain band of frequencies being passed through, so band pass filter. Outside of that band, everything is blocked, meaning V out goes to 0. Band pass filter. Make sense? Right? If I take band of frequencies, V out, starting from 0 all the way to a particular frequency, I allow V in to pass through the output. And after that particular frequency, and I will talk about what that is just the next few slides, everything else is blocked. So you have this band pass filter where a certain band of frequencies is allowed to pass through, and band pass filter. Everything else is blocked, meaning V in or V out goes to 0. Okay, here V out has some value. Outside of this band, V out is equal to 0. Does that make sense to everyone? Right? Same thing here. Starting from 0, going all the way to a certain frequency, everything is allowed to pass through. After that frequency, everything is blocked, meaning after that frequency, the frequency of the input signal increases, V out will be equal to 0. So any frequency that is lower than this frequency is allowed to pass through, meaning low frequencies are being passed, high frequencies are blocked. And hence we call this as a low pass filter. Does that make sense to everyone? Yes. Yes. So yeah, that was going to be the next drawing. Basically, if we draw something like this, frequencies that are higher than this particular break frequencies are allowed to pass through. Anything that is lower is blocked. So high frequencies are passed. And so high pass filter. We will talk about that in just a few slides. Yeah, it's called the break frequency again, but as you look at the next circuit, that's when we'll talk about that. It's called the break frequency or the cutoff frequency. So low frequencies lower than this particular cutoff frequency is allowed to pass through. In a high pass filter, frequencies that are higher than the cutoff frequency are allowed to pass through. It'll be exactly opposite of a band pass filter, meaning that particular frequencies will be blocked, everything else is allowed to pass through. Real life example of a band stop or band reject would be like a line filter, 60 hertz line filter. So if you have our power outlets and you connect it to, like, let's say audio system or any electronic device, that 60 hertz frequency signal from the power line will interfere with the operation If you're connecting a speaker to it, you might hear some interference noise. And so a 60 hertz filter, like a band stop filter at 60 hertz, is going to block that signal from interfering with your circuit. So that's an example. Another example would be if you ever try to charge a audio device in your vehicle and try to listen to sound at the same time, you might hear the engine whirring sound coming out from your speakers. Anyone ever have that experience? No one? It forms like a ground loop and the engine noise comes out through your speakers. And we eliminate that by using a band stop or band reject filters. All right, any other questions? Let's look at our first circuit, RC low pass. Simple circuit. It's a series connection of a resistor and a capacitor. You have input voltage being applied. We're taking the output across the capacitor. Now, not going to do the entire derivation. Again, I'm not going to ask students how to derive anything in the exam, right? But I will walk you through the derivation itself using phasor techniques and techniques that we learned in chapters 1 and 2. The series circuit, right? So what is the total ZEQ as seen by the source? R plus ZC, right? Impedance of the capacitor. Then current I is V in over ZEQ. And output is taken across the capacitor. So V out would simply be I times ZC. V out is I times ZC. You'll have V in here in this equation. You take V in on the other side, you get V out over V in, H of F. When you reduce that equation, you get this. H of F is 1 over 1 plus J F over FB. It's a pretty standard equation. If you take a look, only has two components, F and FB. F is a variable, FB is a constant for that particular circuit. F is the frequency of the incoming input waveform, means H of F at any particular frequency, you plug in that frequency right here as F. FB is a constant given by 1 over 2 pi RC. 1 over 2 pi RC. So it depends. Filter design basically deals with determining the exact values of your components. The cutoff frequency, this FB is known as the cutoff frequency. So FB, actually FB stands for break frequency. And in some other books or some other references, you would see cutoff frequency, FC. Our book uses FB for break, and so I'm going to use FB for break. But keep in mind, if you use a different book, or if someone else talks about cutoff frequency, they're talking about the exact same thing. They're the exact same thing, no difference. Let's use the handy dandy table and perform a quick and easy analysis. When F is tending towards 0, what happens to the capacitor? Capacitor becomes open. What is V out? V out is equal to V in, right? V out is equal to V in. What happens when F is equal to infinity? Capacitor is a short circuit. What is V out? It's a short circuit and you try to measure the voltage across a short circuit. What do you get? Potential difference is 0, right? So V out is equal to 0. So let's take a step back. F0, when frequency is low or F tends towards 0, V out is equal to V in, meaning my low frequencies are allowed to pass through to the output. Make sense? So it's a low pass filter. This is allowing low frequencies to pass through. High frequencies, when F is equal to infinity, V out is suppressed, goes to 0. So high frequencies are blocked, low frequencies are allowed to pass through. So it's a low pass filter, quick and easy analysis. But you have to proceed step by step, right? You plug in F is equal to 0, redraw the circuit. You plug in F is equal to infinity, redraw the circuit again, then take a look at the output. What happens to the output? And then you can predict what the behavior of the circuit is. So again, quick and easy analysis. You simply take the components, analyze the behavior of the components at 0 and infinity, and then predict what the output is going to be. Now, same circuit, the same circuit. V out is here. What if I take V out across the resistor? What happens? Any guesses without performing any technical analysis? A few minutes ago, I said we're studying two circuits, not two circuits. We're studying the same circuit, but low pass. And then if you take the output across the resistor, let's see what happens. F is equal to 0. Capacitor is open. If output is across the resistor, V out is equal to 0, meaning low frequencies are blocked. Let's go to infinity. When it's infinity, what happens? Short circuit here, outputs across the resistor, what happens? V out is equal to, so high frequencies are passed through. Exact same circuit, output across the capacitor is a low pass, output across the resistor, high pass. No different. 2 for 1. RC high pass. It's the exact same circuit. It's just schematically we are drawing it in different place. Output is across the resistor, but the exact same circuit. It's a series connection of a resistor and a capacitor, no different. It's just the location of the output is different, that's all. The transfer function is now different. You have J, F over FB in the numerator. FB remains the same, 1 over 2 pi RC, no change. Okay. So high pass filter, the transfer function has a quantity in the numerator, J, F over FB. Denominator remains the same. FB is still the same, 1 over 2 pi RC, no change. All right, any questions? I have a couple of announcements, but before that, any questions? Any questions at all? Okay, so 2 minutes left, 2 announcements. I need students to fill out the survey for the common final. Again, common final is on Saturday. If you're planning to take it, you indicate it on the survey. If you're not planning to take it, again, indicate it on the survey. You can take it, you can take the common final, or you can take your regular scheduled final. I think for 04, it's on what, Friday? Or somewhere. Now, if you don't want to take the common final, and if you don't want to take it on Friday, again, there's an additional question on the survey. You need to explain why you want to take it with a different section, meaning if you don't want to take the common final, you don't need to explain. You don't need to explain. It's fine. Just indicate no and show up on Friday. That's fine. If you want to take it on Monday or Wednesday, you need to explain why, because only have limited seats. So please go ahead and fill out the survey as soon as you can. Second announcement, evaluation period is now open for the courses and for the instructors. So go ahead and fill out the evaluations. As an incentive, I provide students extra credit in the amount of the participation rate. This is what we see. Okay, this is what I see at my end. Okay. Okay, this is all we see here. We don't even get these evaluations back until the beginning of next quarter. Okay, all we see is basically how many students I have in my class and how many people have responded. So right now it's 5 of 36. So 5 divided by 36 is the amount of extra credit that everybody gets. If this gets up to 18, everybody gets 0.5 points. If this gets up to 36, everybody gets 1 extra point applied directly to your final grade. Meaning if you end up with an 89, it bumps you up to A minus. So the more people who participate, the better it is for everyone. Even if you don't participate, even if you don't fill it out, you're still benefiting because everyone else is doing it. So it's a community effort. All right. Again, it's very important to me personally, also to the department. It goes in our official files, right? And so for me personally, I look at it as ways to improve. So many of the things that I do today is because of something that someone might have written like 2 years ago, or something that someone gave me feedback like last quarter. And so every time we're constantly trying to improve ourselves. So this is very important, not just for my class. It's important for like all classes and all professors. Okay. It's a way to give feedback on where we can improve. If you're doing something good, then reinforce, that your feedback will reinforce that, okay, we are doing this good. If something needs to be rectified, we need to, rectify and correct it. So please go ahead and do that. And again, as I said, as an incentive, every student in the class gets a extra credit in the amount of the participation rate. Yes. It's only section 4. Yeah. I mean, I was pointing to the wrong thing, but yeah. Yeah. Mm.